In this lecture, we will be looking at the estimation of parameters in an autoregressive 1 or an AR1 process. First, let's recall what it means to have an AR1 process. So first we assume a sequence of white noise terms. So these epsilon sub i's are white noise, mean zero, variance, sigma sub epsilon squared. And this can hold for either a weak or a strong white noise. So remember, weak white noise just means that they have the same mean and variance. A strong white noise would be something like them having the same distribution. In either case, they're uncorrelated in time. An example of a case where you have a strong white noise would be if these are, say, Gaussian. Okay, so you have your sequence of white noise terms. We then define the AR1 process to be a sequence y1, y2, y3, such that for some parameters mu and phi, we have this defining equation here. So yt minus mu is phi times yt minus 1 minus mu plus epsilon t for all integer values of t. Recall that intuitively the way we thought of this is if you think of t, say, in days, you can think of this as the difference between today's observation and the mean is equal to some new random term, that's from your white noise, plus some memory of the difference from yesterday's observation and the mean of the process. And that memory parameter phi you can think of as how much of yesterday's deviation is retained. We tend to work with cases where phi in size is smaller than 1. So think of phi as being between 0 and 1. You can think of it as a percentage of memory from yesterday. So if phi is 0.5, today's deviation from the mean remembers 50% of yesterday's deviation from the mean. So that was our AR1 process. But the issue now becomes, what if you actually have data? So you have time series data, and you want to fit that data to an AR1 model. Again, the defining equation for the AR1 model given here postulates that we have a mu, the mean of the process y, and phi, this memory parameter. But if we postulate that this time series data actually follows this model, there has to be a mu and a phi associated with it. So how do we estimate that mu and that phi from the data? And the answer comes in the way of the least squares approach. So we define a function of the two parameters, mu and phi, as the following. This function here, if you note the following, the term inside the square is nothing more than that epsilon t. So you see, if you were to subtract this phi times quantity yt minus 1 minus mu from both sides of this defining equation, solving for epsilon t, you obtain exactly what's inside the square here. So the way that this can be thought of is that you are minimizing, well, we haven't talked about that yet, but that's what we're going to do with this function. You have the sum of the squares of the noise terms. And so we want to minimize that sum of squares. If you recall back from your studies of calculus, this will be obtained by taking the partial derivative of f with respect to mu and setting it to 0, and the partial derivative of f with respect to phi and setting it equal to 0. And these were what we call the first order conditions So if you want to find a minimizer of this function, it has to be the case that the gradient of the function equals 0, i.e. the first order partial derivatives with respect to these two variables are 0. That's the first order necessary condition for a minimizer. But with a least squares problem, this is a convex function. And that means in this case, right, so for least squares, these conditions are also sufficient conditions. And roughly speaking, you can think of it as when you have a convex function and everything's differentiable, you can think of that as being concave up everywhere. And that means if it's concave up on its whole domain, if you find a tangent line, then you have to have found a global minimizer. In this case, what you really have is a paraboloid and now instead of a tangent line, what you're finding is a horizontal tangent plane. And the point at which that horizontal tangent plane exists, that gives you the values of mu and phi that minimize this sum of squares. So through this procedure, we obtain our estimators. We call them phi hat and mu hat. And this intuitively should be natural because essentially what you're doing, if the model fits on average, when you bring this term to the other side and you get the epsilon t's, on average that term should be 0. And remember that the white noise process itself had a mean 0. So you're trying to find a phi hat and a mu hat that gets each of these terms to be close to 0, and then we have to answer a question as to whether or not it's a reasonable fit. That comes next. This minimization problem gives us these solutions, which we call our estimators. But once you have those estimators, you can then go back to that defining equation. So remember, this was just a modified version of the defining equation for an AR1 process. But now that we have estimators for phi and for mu, we can plug those in and get what you can think of as the sample versions of the white noise terms. Those are what we call the residuals. So those are estimators of the theoretical white noise terms. And this is how we obtain them. So again, you just take this defining equation for the white noise terms in terms of the AR1 process and plug in, instead of the theoretical mu, put in the estimator. Instead of the theoretical phi, put in the estimator. And you do this for t equals 2, 3, up to n. So now that you have these residuals, you can think of those as a sampling from the white noise process. So this comes back now to, was this an appropriate model? Remember that we started with the idea that we have this theoretical AR1 process and we have a data set, and we want to fit that data set to this AR1 process. We have well-established machinery to do so. But once you do that, the question becomes, was this the right model to use? if it was, this defining equation should hold in a statistically significant manner for your data points for your residuals. By that we mean these residuals should look like a sample from the theoretical white noise process. So for example, suppose that your theoretical white noise were Gaussian. So each of these epsilon i's was normally distributed with mean 0 and some fixed variance, say sigma squared. And since they're a white noise, they're uncorrelated. The question you would ask would be, do the residuals appear to be a sample from this white noise distribution? So they should pass statistical tests of being normally distributed, coming from some distribution, this distribution, and they should pass tests of being uncorrelated. So you would want to look for correlation in time amongst these residuals. Remember, we had our autocorrelation function. So you can look at the autocorrelation function, and if you see correlation between these, or if they don't appear to be coming from a normal distribution like this, either of those cases would be evidenced against the AR1 model being a reasonable fit for the data. So this is a natural way on the back end, after doing a fit, to check if your choice of model is appropriate. And this line of reasoning actually holds with any fit for a model for time series, which we'll discuss in other contexts.